Hello again and welcome to the ramp. It's a beautiful morning here in London and our aircraft is sitting here ready for this journey. You now have the power and knowledge to jump in and get a great start to the flight portion of the training. All your hard work has led you to now. As a few items of business before jumping on the flight deck, then doing the walk around, let's do several simulator based items first. Pressing my keyboard shortcut, I'm going to request refueling and our catering services. Now those services will pull up to the aircraft and do their thing. And while they do that, let's get to the walk around. Our wheel chocks are set and we don't want to get into any flows yet. So now we can actually go in and do the walk around. Now a walk around would normally be done when one member of the flight crew is underway with the flows. However, as it is just you in command today, we're going to do it now so to ensure that we don't jumble through the walk around begins beside the entry door on the forward left side of the fuselage. As well as making sure the skin of the aircraft is undamaged, we're also checking the 3 probes attached to the left forward side of the fuselage here. Just underneath the jet bridge is the total air temperature probe, which feeds temperature information to the ADIRUs, which in turn compute and indicate it to us via the total air temperature on the primary flight display. So the TAT, as it's called, or you can call it total air temperature, is also used by the ADIRUs in altitude and airspeed calculations. Moving forward, we come to the alpha vane. This measures the current angle of attack to the oncoming airflow and communicates with the left ADIRU, which then determines stall margins and drives the angle of attack indicator on the captain's PFD and HGS. You can see that it's drooped at the moment as there is no airflow over it, but in flight it'd be in a more... Below the radome is the hatch for the electronics and equipment bay, which should be latched tight. The E&E bay houses critically important systems, so we'll have a big headache if things start falling out of it. Moving further aft to the nose wheel and the nose wheel well, check the tires and wheels. There should be no hydraulic leakage on the gear strut, and the strut should not be fully compressed. Don't forget that it needs to provide suspension during taxi, takeoff, and landing. There is a single taxi light on the nose gear. Check that the glass is unbroken. Moving up to the actual nose wheel well, check that the linkages for the doors are in place and intact. In the roof of the well, check that the 2 wheel snubbers are in place. There are no brakes on the nose wheel, so these snubbers slow the wheel or wheels to stop when the gear is retracted. If you look carefully, you can actually see rubber on the snubbers from past gear retractions. Interestingly enough, these are actually made with asbestos, so don't touch them. Moving out of the wheel well and up onto the right forward fuselage, we will do similar checks to this side, with a couple of items added. The top probe is the first officer's pitot probe. This functions identically to the captain's equivalent. However, it sends its data to a different air data module, which then sends electrical signals to the right ADIRU. This means that there is no cross connection between the 2 pitot-static systems, so the 2 PFDs get their airspeed data from separate sources. This is in the name of redundancy. Below the first officer's pitot probe is the auxiliary pitot probe. This feeds the standby airspeed indicator. In our case, that indication is displayed on the integrated standby flight display. There is no crossfeed of information from this probe. These ports measure static pressure, which is used along with pitot pressure to determine speed and altitude. The top port is the captain's static port and feeds data via the air data module to the left ADIRU, which then drives his airspeed indicator. The bottom port is the first officer's static port, which does an identical job but via a different air data module to the right ADIRU, which drives the first officer's airspeed indicator. These ports must be able to access airflow in a relatively undisturbed area, so the surrounding area must be kept clean and smooth. Moving down now, we come to the third static port on this side of the fuselage. This is the alternate static port, and together with the auxiliary pitot probe we saw earlier, feeds the standby altitude and airspeed. After the forward cargo compartment door is the wing illumination light. Moving back towards the wing route now, we have several more items to check. Inlets for the ram air system are located below each wing route. We are looking at the right-hand side inlet at the moment. Check that the deflector door is fully extended. The deflector door prevents slush from entering the inlets on takeoff and landing, and are extended automatically when the air-ground safety sensor indicates that the aircraft is on the ground. They should therefore be extended at this time. Behind the deflector door is the inlet door. On the ground, the inlet doors should be fully open. We'll check the left-hand inlet door and deflector doors when we get around to the other side of the aircraft, which will be in several minutes here. Check that the drain mast is secure and that there is no ice buildup on it, but today with these temperatures that shouldn't be an issue. We have some lights to check here. The 737 has both fixed and retractable landing lights. The retractable lights are located on the belly and are retracted at the moment. Moving up the wing route, the fixed landing light is embedded here, along with the runway turnoff light. Check that the glass is clean and intact. We have leading edge flaps inboard of the engine. Check that they are undamaged and that their position corresponds to the flap position in the cockpit. In our case, they are retracted. They may hang out slightly with hydraulic system B unpressurized, however, this is not the case today. For the engines on the 737NG, we have leading edge slats outboard of the engines. Check that they are in good condition and are retracted. The starboard wing houses the refueling panel. The key point for us here is that the access panel is closed and latched. On the surface of the wing, we can see that there are 4 flight spoiler panels that also provide roll control. Spoiler deflection is initiated when the control wheel is displaced by more than approximately 10 degrees. They can also be extended in flight to destroy lift and induce drag, allowing for faster rates of descent and deceleration. The captain's control wheel is connected by cables to the aileron power control units, while the first officer's control wheel is connected to the spoiler power control units. The 2 control wheels are of course connected, but this system allows roll control redundancy in the event of either ailerons or spoilers becoming jammed. Both the ailerons and the spoilers are moved with the help of the hydraulic system under normal conditions. Moving back down to eye level, let's run through the flaps. The 737NG has double slotted flaps on the trailing edge, which are extended on takeoff and landing to create extra lift, and in the case of approach and landing, drag as well. One important thing to note is that the flap positions that you set as the pilot do not correspond to the actual degrees of flap extension. 1, 2, 5, 10, 15, 25, 30, and 40 are simply units of flap. This gives commonality with the older 737s. Even though the design should be removed, these pins, 1 in each landing gear strut, prevent the gear from being raised. So it is important, obviously, that they are removed before flight. They are actually stored on the flight deck, so if you see all 3 up there on the flight deck, that's a pretty good indicator that they've been removed from the gear. Always best to check just in case. Check inside the wheel well that there is no obvious panel damage. Confirm on the forward wall that neither the System A nor B hydraulic reservoirs are ruptured. System B is the larger reservoir, by the way. On the back wall, perform the same check on the standard reservoir. Finally in here, confirm that both gear actuators are intact. Let's move further aft now toward the tail, Series NGs, as they are the longer variants where tail strikes are more likely. The Dash 400 also had a tail skid. This version of the tail skid only protects the aircraft during takeoff, not landing. The short-filled package 800s and 900 ERs have a tail skid that extends a further 5 inches for protection during landing due to lower landing speeds on those aircraft. Now, Honeywell GTCP 131-9B auxiliary power unit mounted in the tail. Fancy model numbers aside, the APU is a gas turbine generator capable of providing electrical and pneumatic services on the ground and in the air. The air intake is on the increase the service life of the hinges. Each half of the horizontal stabilizer houses a logo light which illuminates the fin. The fin is a large structure which aids the directional stability of the aircraft and plays a crucial role in the event of an engine failure after takeoff. Attached to the trailing edge of the fin is a single-piece rudder, which provides yaw control about the aircraft's vertical axis. Without further ado, let's get this show on the road, or airway if you prefer. Today we start with the originator flow, also known as the receiving flow. It is performed by flight crews when they receive the aircraft in a cold and dark state, as you have today. Firstly, check that you have all dispatch papers on board. We've already gone over this, so I'm assuming at this point that it is accessible. We will certainly need it throughout the flight. Move up to the electrical metering panel on the forward overhead and confirm that the DC metering knob is set to BAT. By doing so, when the battery is turned on, its current and potential difference can be monitored, therefore allowing the flight crew to confirm normal DC electrical system operation. Turn on the battery now by closing the battery switch guard located below the DC metering knob. You will notice with all guarded switches on this aircraft that when the guard is closed, the switch is in its position for normal operation. Switching on the battery will energize the battery bus, switched battery bus, DC standby bus, the static inverter, and thus the AC standby bus. Note here that if the standby power switch is not in the auto position, only the battery bus and switched hot battery bus will be powered. The latter of these is not to be confused with the hot battery bus, which remains powered regardless of switch position to allow power to be provided to essential systems such as fire suppression at all times. The DC meter reads 24 volts. Now check that the gear lever is down and 3 green lights are illuminated, indicating that the 3 trucks are locked in position. Any indications to the contrary would be a major maintenance issue that would need to be addressed immediately at this early stage in the aircraft setup. It's now time to test position. Now for the next step, it is time to align the inertial reference system, or IRS, which uses the inertia of the plane's motion to calculate its position. Although today, this cross-references with the global navigational satellite system for maintained accuracy throughout the flight. We like to do this early on in the proceedings as it takes around 10 minutes to align, and we don't want it keeping us waiting near our time of departure and result in us missing our slot. That's what passengers are for after all. Twist the 2 knobs on the mode selector unit through a line straight to nav. Upon doing so, the on DC light will illuminate as a self-test. However, were this to occur in flight, the implications would be serious, as it would indicate that the IRS was running off battery power, so would only be available for a finite amount of time. Now to the forward overhead panel, arm the emergency exit lights by closing the guard. On the pneumatic panel, we will check that the recirculation fans are off, along with the packs, the isolation valve is open, the APU bleed is off, and the engine bleeds are on, verifying again what we did before. 6 right to take yourself to the position initialization page. This is where we link the FMC with the IRS information and make sure they are fully aligned in our exact position. Enter into the scratch pad, Echo Golf Kilo Kilo for Gatwick, and push line select key to left to enter it in the reference airport. To get current position data, push the next page function key to take you to the position reference page. We'll check that the aircraft's position lights are in the correct position at this stage. All that should be on here are the position lights in the steady position. If it were nighttime, we'd want to use the logo light when it is common to see the systems automatically turn off to prevent overheating, a condition which is deemed to be present, by the way, when window temperature is in excess of 62 degrees Celsius. Can be accomplished here, a short one and a comprehensive one. And to perform the short test one, push the button momentarily and wait for the RL alerts to be heard. To perform the long one, which tests every RL alert in the aircraft, Hold the test button until the alerts are heard. Today we're going to go for the long one, so push and hold that button until Betty awakens.
Glide slope. Pull up. Wind shear. Wind shear. Wind shear.
40.
Terrain.
30. 20. 10.
Wind shear. Wind shear. Wind shear. Too low. Terrain.
Simply an opportunity with as a crew to get on the same page about today's flight information and have a marriage of minds ahead of time for those critical, time-sensitive moments. Obviously, at this stage, you will have already gone through all of the pre-flight stuff. Your crew member will be there, and so they should be familiar with everything anyway, but you do want to talk about the potential emergencies ahead of time and just brief last minute what the expected courses of action are if those things were to happen.